Welcome to my channel. Today we're exploring visual autoregressive modeling, a revolutionary approach to generate images. This paper was published in 2024 by scholars at Beijing University and ByteDance. Stick around to see how this changes the game. Traditional image generation models such as diffusion model and raster scan AR model have been effective but slow and computationally expensive. They struggle to balance image quality and inference speed. They use the next image token prediction, just like text generation. Image tokens are generated in a raster scan order, from left to right, top to bottom. The flattening disrupts the spatial locality inherent in the image. The new visual autoregressive modeling, or VAR, breaks away from the traditional strategy used by language models. Instead of generating one pixel at a time, VAR works scale by scale, starting with rough outlines and adding details step by step. This approach allows autoregressive transformers to learn quickly and generalize well, surpassing diffusion transformers for the first time. On benchmarks like ImageNet, VAR achieves a freshet inception distance of just 1.73, outperforming diffusion models with 20 times faster inference. But what sets VAR apart from others? Let's dive into how traditional models are trained first. A traditional image generation model predicts the next part of an image, one small piece at a time, based on what it has already seen. This is called next token prediction. To process an image for model input, the raw image is passed through an encoder, which converts it into a feature map. Think of this as summarizing the image into a grid of meaningful chunks. The feature map is then quantized using a process called tokenization. A codebook, which is like a dictionary of fixed values, is used to assign a token to each chunk of the feature map. For every chunk in the feature map, the nearest value in the codebook is selected as its token. This is done using a lookup function. Once the image has been converted into tokens, they are arranged in a grid. The 2D grid is then flattened into a 1D sequence row by row, just like how we read text. The model then learns to predict the next token xt in the sequence based on previous tokens x1 through xt-1. The formula means that the probability of the entire sequence depends on predicting one token at a time, given the previous ones. During training, the model compares its predictions to the actual tokens and adjusts itself to improve future predictions. To improve the model, a loss function L is used to measure how far off the predictions are from the actual tokens. The goal is to minimize this error. The loss function has several parts. Im minus Im hat square is the reconstruction loss. It measures how close the reconstructed image is to the original image. F minus F hat square is the map reconstruction loss. It measures how close the reconstructed feature map is to the original feature map. This element ensures that the feature map is preserved during the quantization and reconstruction process. Lambda PLP of Im hat is the perceptual loss. It ensures that the reconstructed image looks perceptually similar to the original image. Lambda P is the weight that controls how much importance is given to this loss. Lambda GLG of Im hat is discriminator loss. It ensures that the reconstructed image matches the original image's style and quality in order to fool the discriminator. Lambda G is the weight that controls how much importance is given to the discriminator loss. This is how the loss function looks like. However, the traditional models face several key issues. The first issue is math premise violation. Tokens in image sequences have bidirectional correlations due to spatial dependencies, contradicting the unidirectional dependency that the traditional models use. The second issue is limited zero-shot generalization. Traditional models struggle with tasks requiring bidirectional reasoning, like predicting one part of an image from another. Third is the structural degradation. Flattening image grids from 2D into 1D disrupts spatial relationships, weakening local correlations. Lastly, the traditional models requires O of n squared steps and O of n to the sixth computational cost, making it computationally expensive for larger images. So, what does VAR do differently? VAR uses next scale prediction. That scales here means resolution. We quantize a feature map into a token map with low resolution first, then repeat the process multiple times, each time with a higher resolution, until we reach the highest resolution. The autoregressive likelihood of RK depends on all prior token maps. During training, we use a blockwise causal attention mask to ensure each RK can only attend to its prefix. Here is the algorithm of encoding. First, we take an input image and extract its feature map F using an encoder. We also start with a blank token map R. Interpolate the feature map from its original dimension to the new dimension HK by WK, then quantize the feature map into tokens. Push the token map RK to R. Use the lookup function to retrieve the corresponding decoded feature map ZK from a codebook Z. Then, use the interpolate function to resize ZK to match the highest resolution, ensuring consistency with the original feature map's dimensions. Subtract the reconstructed information phi-k-zk from the current feature map F. This step ensures that subsequent predictions focus on capturing the residual details that were not accounted for at earlier scales, improving overall generative accuracy. Imagine these steps as an artist studying a subject, identifying its essential components, shapes, colors, textures, and spatial relationships, and crafting a mental blueprint that transitions from broad, general features to intricate details. The final output is a list of token maps, R, representing the image at K different resolutions. With the token maps R, we then reconstruct the image with the algorithm too. Just like painting, we start with a blank canvas, meaning an empty feature map F hat equals 0, and gradually add more details to it. The QPOP function extracts the next token map RK, ensuring that the algorithm processes the token map sequentially from low resolution to high resolution. Use the lookup to find the corresponding codebook values. This step translates the quantized tokens into meaningful image features. ZK is then resized to the final resolution HK by WK using interpolation. This ensures that the feature matches the scale of the final image. The adjusted feature ZK is then passed through a convolutional layer, or phi-k, to refine it. The result is then added to the feature map F to incrementally build the image. This process is repeated for every stored token map in R, progressively adding finer details to the canvas. Once all chunks have been processed, the feature map F is passed through a decoder D, which transforms it into the final reconstructed image, IM hat. Lastly, does VAR follow scaling laws? Also, what are scaling laws? Scaling laws describe how a model's performance improves when model size, training data, and compute resources increase. When developing large models, scientists often analyze scaling laws to understand how to best allocate resources of these three elements to achieve the optimal performance. Research has established that autoregressive LLMs follow scaling laws, which means scaling up autoregressive LLMs leads to lower test loss L, which is a function of X, where X can be parameter counts, training token size, and compute resources. A log transformation to L and X reveals a linear relation between log L and log X. This formula makes it easier to fit a straight line using linear regression. The researchers of this paper set up experiments with 12 different model sizes ranging from 18 million to 2 billion parameters, training tokens up to 305 billion, with training epochs ranging from 200 to 350. They then fit the data to find the slope using linear regression. Here is the result of the experiments. Different blue lines denote different model sizes. X-axis is the training compute. The y-axis is the loss measured by test loss and token error rate. Since the slope is negative, VAR follows the power law scaling laws. Here is a comparison of images generated with different parameter counts and training compute. Higher compute and more parameters result in better image quality. And that wraps up our deep dive into visual autoregressive modeling. We've seen how this framework takes image generation to the next level, outperforming traditional AR models and even diffusion models in quality, efficiency, and speed. With its scalability, robust performance, and potential for text-to-image and video generation, VAR is shaping up to be a game-changer in multimodal intelligence. If you found this as exciting as we did, don't forget to like, subscribe, and let us know your thoughts in the comments below. Thanks for watching, and we'll see you in the next video.